All right, today we're going to be calculating the gravitational field strength at the moon's surface based on the moon that may be considered to be a uniform sphere isolated in space with a radius 1.74 by 10 to the 3 kilometers and a mass 7.35 by 10 to the 22 kilograms. We do this calculation today in honor of the Artemis missions, a little bit of Greek mythology, Apollo and Artemis, twins. Okay, so the Apollo missions and now the Artemis missions. We're going back to the moon with the goal of eventually making it to Mars, where we just flew a helicopter. What a time to be alive. Speaking of times to be alive, Newton, a few hundred years ago, came up with the law of gravity, G(m)(m) over r squared. Newton also had this second law of motion that said force equals mass times acceleration. So let's think about the acceleration due to gravity. The force of gravity is equal to mass times the acceleration due to gravity. The gravitational field strength is equivalent to the acceleration of free fall, right? So we're going to equate the force of gravity with Newton's law of gravity with Newton's second law. Realize that on the moon's surface, or on the surface of any planet or object, it doesn't matter how massive the thing sitting on the surface is, right? What matters about the gravitational field strength is the mass of the moon itself, which is given here. So we've solved for the acceleration due to gravity as Newton's universal gravitational constant times the mass of the moon divided by the distance that some object on the surface of the moon is away from the moon squared. And so because we can consider it to be a uniform sphere, right, we can collapse all of the mass, all the 7.35 by 10 to the 22 kilograms down to the center of the moon and say, what is the field strength at the surface if you're this many kilometers away from the moon, even though you're standing on its surface, right? We're sort of saying, well, the moon is really existing at its center, all of its mass is there, sort of the way we do the calculation. All right, so G is 6.67 times 10 to the negative 11. I'll leave the units as Newton meters squared per kilogram squared. I got the mass, the moon, 7.35 by 10 to the 22 kilograms. And divided by the radius, let's put it down here, 1.74 times 10 to the, I don't know if you guys are going to be ready for this, 6. Oh, you made a mistake. It's a 3. Oh no, what I've done here. Kilo. Okay, so kilo itself is 10 to the 3. So it's 10 to the 3 kilo meters. My units of G up here are meters squared, right? And so I've just kind of done a quick conversion of saying, well, if there's 10 to the 3 times another 10 to the 3, like this kilo is just an extra 10 to the 3. So 10 to the 3 times another 10 to the 3, 1,000 times 1,000, that's a million. 1.74 million meters squared. Right, don't forget the square R. It's an inverse square law. So the meters squared will cancel here. This kilogram will cancel one of these. Newtons per kilogram. Bingo. Got the units I want. That's a check on my calculation. Like, yeah, I didn't make any mistake, you know, with my working. And now we're about to know how strong gravity is on the moon. 6.67 times 10 to the negative 11 times 7.35 by 10 to the 22 divided by open parentheses 1.74 times 10 to the 6 squared equals 1.6. Just to compare that to Earth, 9.8 newtons per kilogram. As a physics teacher, I have nice metric mass. I am 100 kilograms of mass, which means that my weight here on planet Earth is 980 newtons. Nice round numbers there, right? 100 kilos. So every kilogram of mass that I possess, gravity is pulling down on me with 9.8 newtons of force because I'm a whole 100 kilos. That's my weight. That's the force due to gravity, my weight here on Earth. if I go to the moon, I'm still 100 kilograms of mass. Those are like the amount of matter I possess. That's intrinsic to me, you know, how many atoms I possess. But on the moon, my 100 kilos would not be multiplied by 9.8 newtons per kilogram, but only 1.6 newtons per kilogram. And so on the moon, I'd weigh only 160 newtons. So your weight changes based on where you are in the universe, but your mass does not. Hopefully. You don't want to lose mass on the way to the moon if you're an astronaut. Your weight might change. That's okay. We understand that. You lose your mass, there's a problem. Maybe you lose a little bit of weight on the way. That's okay. A satellite is in a circular orbit about the moon at a height of 320 kilometers above its surface. Calculate the time for the satellite to complete one orbit of the moon. All right. Circular orbit. What do we know about things moving in circles? So I'll draw myself a circle. I'll draw myself a circular orbit. The distance of that orbit is equal to like the radius of the orbit times pi times 2. Or we usually write that as 2 pi r, right? The circumference of a circle. Distance divided by time is the speed, the velocity, okay? And if we take the force that's required to keep the object moving in a circle, the centrifugal force, which is equal to mv squared over r, where m is the mass of the satellite. And if we say that the centripetal force pushing this massive satellite towards the center of its circular orbit is provided by gravity, mm over r squared, then we can solve for this velocity. This velocity squared as gm over r. And we know the radius of the moon. It was given a moment ago, is like 1 point something by 10 to the 6, 1.74 by 10 to the 6. And we also know how much higher above the surface we're putting this satellite. So keep that in mind. We saw it. Sometimes it's just very simple, and they're giving you what's the radius of the orbit, and that's what's understood like from the center of the object. Here, we know what the radius of the planet is, or the object of a moon in this case, plus the height of the orbit. So we're going to have to sort of consider that too. But we're solving for time, and so let's introduce that into our equations here. So if v is 2 pi r over t, then v squared, we'll just plug all that in over here. So we've got 2 pi r over t, which is the velocity, but it's squared. And that's equal to gm over r. So that becomes, as we've seen many times, 4 pi squared r squared over t squared equal to gm over r. And now we'll move t squared up here to this side of the equation, and we'll multiply by an r over gm. So times it by r, times it by g, times it by r, and then divide it by gm. So we do the same thing to both sides. So g's cancel, m's cancel, r's cancel, and we've got the time squared equal to, if you can keep track of that mess there, 4 pi squared r cubed over gm. You've seen how we've used this equation to solve for r cubed. We use it to solve for m. We can solve for t. And can we use it to figure out pi? Like, let's make it, let's measure everything and then use this as a way to solve for pi. I don't know if that would give us a good way to get to pi or not. Take a square root. Don't forget to take your square roots and your cube roots, right? If you're solving for R or T there. Sorry, everybody, yesterday. Forgot to take a cube root. All right, let's make some substitutions. So this is going to be T equals 4 pi squared R cubed over GM to the 1/2 power, right? That's how we can take the square root. We need to calculate R. So what is this radius? The radius is 1.74 by 10 to the 6 meters to get from the center of the moon to its surface, plus another 320 kilometers. So we can add 1.74 by 10 to the 6 plus 320 times 10 to the 3. And we get 2.06 meters. And now we've got everything we need to solve for time. So we've got 4 pi squared. R is 2.06 by 10 to the 6 meters cubed over 6.67 by 10 to the minus 11 times the mass of the moon. Who remembers that? .35 by 10 to the 22. 3 minutes left in class. Plenty of what we're solving for, seconds of time, but we have to work diligently here. So 4 times pi squared equals times 2.06 by 10 to the 6 to the 3rd equals divided by 6.67 by 10 to the negative 11 equals divided by 7.35 by 10 to the 22 equals. I'm getting 7.04 by 10 to the 2, 3, 4, 5, 6. Didn't take the square root. Like, wait a minute. This is a long time. Like 53 years. (8,390 seconds). Final answer. 2.3 hours. All right, that seems more reasonable. Always think about the reasonableness of your answers, and we'll see you next time.